In this lecture video, we will discuss about the mean value theorem, the generalization of the Rolle's theorem. Let f be a function such that f is continuous on the closed interval a to b and f is differentiable on the open interval a to b. Then there exists a number c in the open interval a to b such that the derivative of the function at c is equal to f of b minus f of a all over b minus a. The mean value theorem is also called the law of the mean. Take note that since the mean value theorem is a generalization of the Rolle's theorem, the third condition of the Rolle's theorem, the f of a is equal to f of b and both must be equal to 0, has been removed for the mean value theorem. Meaning to say, the theorem will not be limited anymore for horizontal tangent lines. Take a look on the graph. We have the tangent line and the secant line, as well as the interval a to b and the number c within the given interval a to b. Geometrically, the slope of the tangent line is equal to the slope of the secant line. This implies that the two lines are parallel to each other. Take note that the slope of the tangent line is equal to f prime of c. So that is, by the definition of the derivative, it is actually the slope of the tangent line at a given point. And the slope of the secant line is equal to f of b minus f of a all over b minus a. So that is y2 minus y1 all over x2 minus x1 by the definition of slope. Our goal is to analyze functions. First is to confirm or to analyze whether the function satisfies the two conditions, and then if yes, we are going to find the value of c. First example. Determine if the mean value theorem applies to the following functions on the given intervals. If so, find all the values of c satisfying the conclusion of the theorem. F of x is equal to x squared plus 2x minus 1 on the closed interval 0 to 2. We have two conditions for the mean value theorem. First, is f of x continuous on the closed interval 0 to 2? The answer is yes. Simply because the domain of f of x is the set of real numbers, meaning to say it is continuous on R, and when it is continuous on R, it implies that it is continuous everywhere. Next, if f of x differentiable on the open interval 0 to 2, the answer is yes, as the derivative 2x plus 2 is defined for all x in the open interval 0 to 2. Since the two conditions are satisfied, there exists a c in the open interval 0 to 2 such that the derivative at that value of x is equal to f of 2 minus f of 0 all over 2 minus 0. Before we plug in the values to the equation on the right, let us solve first for the individual values. For our f of b is equal to f of 2. That is equal to 2 squared plus 2 times 2 minus 1. That is equal to 7. Next, substituting 0 to x squared plus 2x minus 1, we have negative 1. And also the derivative, we have f prime of x is equal to 2x plus 2. Substituting the value of c, 2x, into the derivative, we have f prime of c is equal to 2c plus 2. We can now substitute these to our equation for the mean value theorem. 2c plus 2 is equal to 7 minus negative 1 all over 2 minus 0. Simplifying, we'll have 2c plus 2 is equal to 8 over 2. Simplifying further, we'll have 2c is equal to 2. So performing division, and then we transpose 2 to the other side of the equation. And then after that, we divide both sides of the equation by positive 2. So c is equal to 1. Because the conditions of the hypothesis of the mean value theorem are satisfied, there exists c is equal to 1 in the closed interval 0 to 2 such that the derivative at x is equal to c is equal to f b minus f of a all over b minus a. The value of c is equal to 1. Next, let's have a rational function here. F of x is equal to 4 over 9 minus 2x on the closed interval 5 over 2 to 4. Okay. First condition is f of x continuous on the closed interval 5 over 2 to 4. The answer is yes. F of x is discontinuous only at x is equal to 9 over 2. And 9 over 2 is not an element of the given closed interval. Because 9 over 2 is 4.5, our interval only has the endpoint 4. Next, is f of x differentiable on the open interval 5 over 2 to 4? The answer is yes, as the derivative is defined for all x in the open interval 5 over 2 to 4. So the restricted value also for the derivative is that x is not equal to 9 over 2. Now let us solve for the f of a, f of b. F of 4, that is our f of b. 4 over 9 minus 2 times 4, that will be equal to 4. And then we have f of 5 over 2. Substituting that to the function, we have 4 over 9 minus 2 times 5 over 2. We have 4 over 9 minus 5, which yields 4 over 4 equals 1. Substituting the derivative and f of b minus f of a and b and a will have 8 over 9 minus 2c quantity square is equal to f of 4 minus f of 5 over 2 all over 4 minus 5 over 2. Performing the operations on the right side, we'll have 4 minus 1 all over 3 over 2. Simplifying further, we'll have 2 on the right side of the equation, and then performing multiplication on both sides of the equation to clear the fraction, we will have 4 is equal to the square of 9 minus 2c. Take note that we divide also 8 by 2. So we have 4. Okay, taking the square root of both sides of the equation, we will actually have two answers here, as the square root of 4 is equal to positive negative 2. The first value of c is 7 over 2, and the second value of c is 11 over 2. Since we are given here a closed interval 5 over 2 to 4, 7 over 2 is within the interval, since that is 3.5. However, for the 11 over 2, that is equal to 5.5, that is not an element of the given closed interval. So here, the value of c is equal to 7 over 2. Example 7, let us have a trigonometric function here. F of x is equal to the square root of 1 plus cosine x on the closed interval negative pi over 2 to pi over 2. Is f of x continuous on the closed interval? Yes, because the domain of this function is the set of real numbers. Take note that the square root of 1 plus cosine x, 1 plus cosine x will always be positive regardless of the value of x. Next, is f of x differentiable on the open interval negative pi over 2 to pi over 2? The answer is yes as well, as the derivative of f of x is continuous, or it exists on the closed interval. Now, since the two conditions are satisfied, to solve for c is left as an exercise. Example 8, suppose f is continuous on an interval I. Use the mean value theorem to show that if f prime of x is equal to 0 for all x in I, then f is constant in I. We will now have a step-by-step proof. We will arrange this later in the compact paragraph form. First, we start by the assumption. Assume f is continuous on the interval I. Next, since we are using the mean value theorem, we have to specify what I is. We have to define what I is. Let I be a closed interval a to b, where a is less than b and both are real numbers. Next, we are now going to assume the premise of the main implication. Assume further that f prime of x is equal to 0 for all x in the closed interval a to b. So we will now use the closed interval here because we previously defined it as a to b, closed interval. Next, since we use the mean value theorem, we will introduce C. Let C be an element of the closed interval a to b. Thus, f prime of C is equal to 0. Since we have the assumption in pink that the derivative for all x is equal to 0. So C is included there. After that, then by the MVT, 0 is equal to f of b minus f of a all over b minus a, which implies that f of a is equal to f of b. Suppose that f of a is equal to f of b and both are equal to k, a real number. Then it follows that f of x is equal to k and f prime of x is equal to 0 for all x in the closed interval a to b. Now, we can conclude since we're already done with our proof. Therefore, if f prime of x is equal to 0 for all x in I, then f is constant in I. This is our proof in paragraph form. For our next examples, we will now apply the mean value theorem in approximation of values of non-integral real numbers. Geometrically, the slope of the tangent line is equal to the slope of the secant line. Thus, we have this equation from our previous discussion. Equivalently, if we will tweak or manipulate the equation and solve explicitly for f of b, we will have the following equation. F of b is equal to f of a plus the quantity b minus a times f prime of c. Now, if we will make b close to a such that c is sufficiently close to a, we see that c approximates the value of a. So, halimbawa, for example, just imagine it. This point, we want to make this as close as possible to a such that this point approaches this point. If that happens, we can see that the secant line actually approaches the tangent line. And aside from that, we can see that the C here approximates the value of A as it becomes nearer and nearer to it. Now, what happens? This implies that f of C, the value of y of this point, is approximately equal to the y value of this point, and it follows that the derivatives are also approximate to each other. The derivative of f at c is approximately equal to the derivative of the function at x equal to a. So habang lumalapit itong point na to dito kay a, itong si c palapit ng palapit kay a, we can take c as the approximator for a, as well as the value of their y, f of c and f of a, as well as their derivatives. Thus, we can replace f prime of c here by f prime of a, since we are approximating it. Therefore, f of b is approximately equal to f of a plus the quantity b minus a times f prime of a. Take note that we use here the double tilde symbol, which means approximately equal to. First example, approximate the value of square root of 26. Our strategy will be to think about a perfect square that is near 26. We will use here the approximation. What do we need here? We need the f of a, f of b, as well as the f prime of a. So how will we get those? First, let us have f of x. Let f of x be equal to the square root of x. Since we have here square root of 26, so we need to have a function that will take this form. The derivative of f of x is equal to 1 over 2 square root of x. Next, let a be equal to 25. Then f of a is equal to the square root of 25, which is equal to positive 5. Here we take the principal root. Next, we need b. Let b be equal to 26. That is what we're looking for. So that f of b is equal to the square root of 26. Also, f prime of a is equal to 1 over 2 square root of 25. That will be equal to 1 over 10. How is that? We simply substitute the value of a here on the derivative so that it will be the value to be substituted here. Next, let us all plug in these values to the approximation. We have square root of 26 is approximately equal to 5 plus the quantity 26 minus 25 times 1 over 10. Simplifying this, we will have 5 plus 1 over 10 and then 5 plus 0.1. Therefore, the square root of 26 is approximately equal to 5.1. The calculator value of square root of 26 is 5.099019511359. Our approximation is a little bit close and accurate but not precise. Next, approximate the value of the fifth root of 33. Using the same algorithm that we did in example 9, here the difference is that this one is in the fifth root form. Strategy, think about a perfect fifth that is near 33. The perfect fifth that is near 33 is 32. That is 2 raised to 5. We will use the same approximation. Now solving for the derivative, f of b and f of a will have, first we have the derivative. The f of x is equal to x raised to 1 over 5. So that is equivalent to the fifth root of x. So that the derivative is equal to 1 over 5x raised to 4 over 5. So we put the exponent on the denominator so that it will be positive. We use the power formula here. Next, let's have the f of b and f of a. Let a be equal to 32. Then f of a is equal to the fifth root of 32 equals 2. Next, b. Let b be equal to 33. Then f of b is equal to the fifth root of 33. So this is the quantity that we are solving for. Next, let's have the f prime of a. So that will be f prime of 32. We have 1 over 5 times the quantity 32 raised to 4 over 5. That is equal to 1 over 5 times 16 equals 1 over 80. We can now plug this in to our approximation. We have the fifth root of 33 is approximately equal to 2 plus the quantity 33 minus 32 times 1 over 80. Simplifying the right side of the approximation, we have 2 plus 0.0125. Therefore, the fifth root of 33 is approximately equal to 2.0125. The calculator value of this is 2.012346617. So this is a little bit close to the real value, to the calculator value. You have reached the end of the discussion. You are highly encouraged to answer the following exercise on the Rawls theorem, mean value theorem, and the application of the mean value theorem.